Hello everyone, welcome back. I am Fer and this video is going to be very different from the videos I usually make because this is an introduction to symmetries in physics. Because I think that symmetries are probably one of the most important concepts in physics, and it is simple enough that it can be understood by pretty much anyone with a basic background in science. But for some reason, we only teach it at the highest levels. For example, I only learned about the things I'm going to teach you here when I was, for example, learning analytical mechanics in my bachelor, and later when I was learning about particle physics and quantum field theory in my master's. And yeah, okay, those topics are very high level and they rely on symmetries, but the topic of symmetries itself is not so difficult, it's not so complex. If anything, it is weird because we are not used to think this way because they don't teach us to think this way. So it might be confusing and it might be weird, but it is not difficult. And once you understand symmetries in physics, it changes the way you look at the world. Because for real, you understand that everything is symmetries. And for example, symmetries in physics can help you understand how we measure things, why we measure things, and why there are things to be measured in the first place. Which I know it sounds very, I don't know, very confusing, very like, but it's everything is going to make sense by the end of this video. Yeah, just trust me, okay? And let's start talking about symmetries, because everyone has a very good intuition of what a symmetry is. Like for example, let's say that I draw two shapes. One is this, and then the other looks a little bit like this, right? And then I ask you which one is symmetric. Even if my drawing itself is not exactly symmetric, everyone knows that this is the symmetric one, like if I were to draw it perfectly. But so the intuition we have about symmetry is really good. But what is like the formal definition? What would mathematicians say? Well, in mathematics, they say that symmetries are an action you can perform onto something that leaves it unchanged. Okay, so for example, in this case, we have this figure here, and we can say, well, one action we can perform to this thing is that we can flip it. We can flip it around this axis, and when we do, the result is exactly the same. You're going to have the same shape as before. And so we call this a reflection symmetry. And the reason we call it a reflection, I mean, it's pretty easy to understand. Let's say that we have a mirror. Here is a mirror. And let's now imagine that you had like a piece of paper, a triangular piece of paper, and then you stick it to the mirror like this. Then the mirror is going to reflect it, and you are going to end up with this same shape. Okay, so that's just one kind of symmetry, reflection symmetry. But of course, there are many other kinds of symmetries. For example, let's say that we have a triangle, and this triangle has all its shapes are the same side. Again, imagine I draw it perfectly. And now let's say that we rotate this triangle. We rotate some amount of degrees. This is a rotation. And the result is that we end up with the same triangle, right? Okay, so this is a symmetry. But you might be thinking, well, okay, I know that the triangle ended up in the same orientation, but it's not like nothing happened. Something did happen. The triangle did move. And so one way we can understand this is that we can put some labels on the corners. So for example, if this is corner 1, 2, and 3, then I can say that after this rotation, everything moved to the right. So for example, now in the top is the corner 3, 1, and then 2. Okay? So just look at what we have just done, because this is really important. Because the labels that we put to the corners are just for our sake, right? These numbers here just help us understand what's going on. But the rotation was happening with or without or labels, right? Or labels are just to help us understand what's happening. Okay, and also you can see how we could have chosen anything else to be the labels. I mean, I could have started maybe instead of the one starting at the top, I could have started here and it would be 1, 2, 3. Or I could have chosen A, B, and C. Like the labels you choose don't. Okay, so whenever you have a symmetry, you have the freedom to choose how you are going to label the elements of that symmetry. Okay, and as long as you are consistent with your labels, that's it. It doesn't matter. Now remember, whenever you see a symmetry, you are free to choose the labels. And the symmetry is just, the labels are just for us to understand the symmetry. I'm making a lot of emphasis on this because this is going to be very important. Because now let's apply these ideas to physics. So for example, I mean, I know that you all have heard about Benjamin Franklin. I mean, many people say that he discovered electricity, but he didn't discover electricity with the sky and the thunder. He did research electricity a lot. He did some important contributions. So electricity was already known at the time, and people knew there were two kinds of electricity. So for example, they knew that if you have two objects with electricity and they attracted, well, if they repelled each other, it was because they had the same kind of electricity. This was known at the time of Benjamin Franklin. And people also knew that if you had objects with different charges, the effect would be that instead they would attract each other. Benjamin Franklin was studying this and he thought, we need a way to keep track of what kind of electric charge we are talking about. And so he made some experiments. And so he ended up naming one kind of electricity positive and another kind of electricity negative. So for example, in this example, we could say that maybe these two electrically charged objects are both have positive charge, and that's why they are repelling each other. And in this other example, maybe one is positive and one is negative. And that's the reason we say that, for example, protons are positive and electrons are negative. And I know that you have probably heard this if you have taken classes about circuits or maybe chemistry. You have noticed that Franklin's choice was a little bit unfortunate. It would have been better if he had chosen electrons to be positive and protons to be negative. Because, for example, in chemistry, you have to say that a proton gains an electron and it becomes more negative. And you are like, okay, I get it, but it's a little bit counterintuitive. Or, for example, electric charge, right? Like electrons move in one way, but we say that electric charge moves on the other way. And it works, but it's a little bit confusing. But the thing is, the physics works the same. Benjamin Franklin could have chosen to label the different kinds of electricity in the opposite way. If he had done that, we would be in a universe in which, well, like you can imagine a different history of Earth, in which Benjamin Franklin called the kind of electricity found in the nucleus of atoms as negative, and the kind of electricity found in the electron clouds as positive. And everything would be exactly the same. The laws of physics work exactly the same. And okay, I know that maybe you have some trouble believing me that this happens, or maybe you believe me, but you still want to see an example. Don't worry, I have you covered. Let's say that there are two objects, right, that have, again, they have electrical charge. And you and your friend are making an experiment. Let's say that this object has a charge that we're going to call Q1, and this is going to be Q2. And you and your friend know that the formula for the force between two objects with electric charge, this is Coulomb's law. This is given by Coulomb's constant times charge 1 times charge 2 divided over the radius squared, the distance between the two objects. This is the radius. And let's say that right now all you and your friend care about is you just want to know in which directions these objects are going to move, if the force between them is going to be positive or negative. Just a refreshment, if it's positive, they are going to move away from each other. If it's negative, they are going to attract each other. Okay, so let's say that your friend tells you, okay, I measure them. So both of them have a charge of 1 coulomb. And you are like, okay, both are positive, cool. And so you go to your formula and you say, okay, Q1 times Q2. So we have 1 times 1 is going to be, well, 1. Okay, so this is positive. So since both are positive, they are going to repel each other, right? The force is going to move them aside. Okay, but then your friend tells you, no, wait, sorry, I made a mistake. It turns out that Q1 is negative. And you're like, okay, fine. It's not a big deal. So then the difference is that you have, okay, minus 1 times 1. Okay, this is negative 1. Okay, so no, you now realize, okay, the force is going to be negative. So they are going to move towards each other. Okay, that's fine. But then your friend tells you, no, sorry, dude, I made another mistake. Sorry, last time. Q1 is positive after all. The negative one was Q2. Sorry, I got confused. And you're like, okay, your friend is making a lot of mistakes, but whatever. So you say, okay, Q1 is positive and Q2 is negative. And the result, look, it's the same. They are still going to attract each other because their charges are still different. But then your friend tells you, no, sorry, dude, finally, last time, both are negative. Sorry, I now, for real this time. And you're like, okay, fine, both are negative. And then you put, okay, so minus 1 times minus 1 is 1. It makes sense because both are negative, so they are going to repel. But now, check this out. Check what happened here and here. The result is exactly the same, but the charges are exactly opposite. Interesting. And in this other case, look, so in this case, we basically switched positive charge for negative charge, and the result didn't change. And here, in these other two cases, we did the same. We changed positive to negative, and we changed negative to positive. And the result was also the same in both cases. So my point here is that, as you can see, the electric force is not affected if we switch the charges. If you switch electric for positive and positive for negative in electromagnetism, the result is exactly the same. And that's always the case. So this is a kind of symmetry, right? And in fact, we can now look, okay, so basically what is happening is that we have one kind of charge, and we can switch it with another kind of charge, and the universe doesn't really care. This is similar to what we were seeing before, where we had like this reflection and symmetry. And so what happens is that both of these examples are examples of reflection symmetry. So that's interesting because it means that you can have one symmetry and it can be expressed in more than one way. And in fact, for example, tons of things have reflection symmetry. Like, I don't know, like a square has it, a circle has it, and many other things. And so my point is that now you can see that back when Benjamin Franklin realized this, maybe he didn't notice it at the time, but the reason he could choose, that the reason he had a choice between positive and negative, that he could have named either charge either way, was because there is a symmetry here. And in fact, look at this. Here. What happens is that the universe is just looking at the symmetry. Because let me go back here to the triangle. Imagine the symmetry is the triangle and the movement. Remember that the labels are there just for our sake, right? The labels, we put them there just to understand what was going on. It's the same thing that is going on in here. Benjamin Franklin just put these labels here to understand what was going on. But the universe doesn't care. The universe doesn't see these numbers. The universe doesn't see positives and negatives. All the numbers that we use in physics, in science, are there just for us. But what is the universe really looking at? The universe is really looking at a symmetry, right? The universe is looking at a symmetry, And to understand that symmetry, we use labels, we use numbers. That's why we can measure things because the universe has symmetries. Measurement is just, whenever we measure something, we're just putting labels to the symmetries of the universe. Okay, so I hope that that's coming across. Please tell me in the comments if that made sense, because I really want that to be really clear, that the universe is full of different symmetries. And whenever we put labels on those symmetries is when we are measuring something. Okay, now in this case, there are many other examples that I would like to use, but this video would be way too long. But keep that in mind. Whenever you learn something in a science class, like, I don't know, chemistry, some kind of engineering, anything else, whenever you see how we are measuring something, whenever you see a formula, it means there's a symmetry in there. Now, that symmetry might be really hard to understand, it might be really hard to find, but believe me, it is there. So I feel like that changed my mind. Like it changed how I looked at the world when I understood this. So okay, so that was the first step in this video. Symmetries, we can measure things because the universe has symmetries. And whenever there's a symmetry, there's also freedom on how to measure it. Oh, and also I want to make a really important point here. This positive and negative thing is a convention. Benjamin Franklin could have chosen the other way around, but it's very useful that everyone in the world agrees that protons are positive and electrons are negative. This is a useful convention, but it is a convention, right? Like God didn't come from the sky to tell us that this is how it should be. No, we were free to choose how to label these things. And science is full of conventions and is full of moments of choice. And so I want you to recognize them. For example, whenever you learn about the right-hand rule, think about, why are we using the left-hand rule? Because it would work. It's just a convention. And it's just, okay, let me tell you about my trauma. It's just, I had a professor once, and we were learning about the right-hand rule and the left-hand rule. And if you don't know what I'm talking about, don't worry. But the important thing is that I asked, why don't we use the left-hand rule? And he told me, oh, because it's in the name, it's the right-hand rule. and I was very angry at that, because I knew his answer was bullshit. It's like, I know it is named the right-hand rule. It's like, he didn't know. But now, but the thing is, now I know. There is a symmetry in the universe, and we can choose, actually, let me explain that symmetry as well. So it turns out that whenever you have a plane, and you need to choose a vector that is perpendicular to this plane, that goes like this, you can choose a vector coming up or a vector going down. This is another symmetry, right? The universe doesn't care. How do I explain it? Yeah, both of these vectors are perpendicular to the plane, right? And so we just had to choose one of them, and we chose the one going up, and that's why we use the right-hand rule. But the left-hand rule also works. And so the universe, for example, whenever you have like the electromagnetic force, because this is important, for example, for cross products. So for example, if you have the magnetic force, this is its formula. It's equal to the charge of an object times its velocity, which is a vector, cross product with the magnetic field, which is also a vector. But this is if you're using the right-hand rule, because if we are using the left-hand rule, it's very similar, but you just have to remember that A cross B is equal to C, so then B cross A is equal to minus C, because with cross products the order matters. And I guess this doesn't make any sense if you don't know vector calculus, but just trust me, that's how it works. And so the thing is that if we are using the left-hand rule, then all we have to do is write first the magnetic field, then the velocity, and this works exactly the same. And remember, the universe doesn't care about right-hand rule or left-hand rule. The universe cares about this symmetry, and we humans have to use these conventions in order to understand the symmetries. But the conventions are independent of the symmetries. Okay, so I think it's enough of that. Because now we have to move to section 2, which is, all about Emin-Noether and the Lagrangian. So let me tell you what the Lagrangian is. So it turns out that a long time ago, Lagrange and Euler discovered this quantity that, well, they called the Lagrangian. Well, Lagrangian discovered it with a little bit of help from Euler. But I guess Euler already had a ton of things with his name, so he was, sure, Lagrange, you can have this one. And anyway, so this is the Lagrangian, and it is very useful because there is this equation, and don't worry if you don't understand it. Right now, I just want to write it just for the sake of the people who know what this means. And if you don't know what it means, I don't know, perhaps you are curious enough to go figure it out, and that would be really cool. Actually, I made a mistake here. There. And then the derivative with respect to time. Okay, the important thing of the Lagrangian is that with these two things, you can explain, sorry, let me do that a little bit better. Okay, so with these two things, you can explain pretty much all of physics. And I do mean like Newtonian mechanics, relativity, quantum mechanics, thermodynamics, if you really want. Everything about physics comes from these formulas. Like, I know it's incredible, and I'm gonna put you some links. You can look more about this if you're curious. But yeah, Lagrangian is incredible. This all comes from the principle of least action, which is a whole nother thing. So don't worry about that. But all I need you to know is that Lagrangian, very powerful stuff, very useful. And that's why Emin-Noether got interested in that. Emin-Noether was a brilliant scientist. She was a German mathematician, and she learned about Lagrangians. She wasn't a physicist, but I guess she got interested in Lagrangians, and she made a key discovery, something that not even Euler and Lagrange noticed. And keep in mind, Euler and Lagrange were some of the smartest scientists ever, period. Euler is probably one of the greatest geniuses in the history of humankind. And he didn't notice this, the thing that Emin-Noether discovered. Emin-Noether discovered that, okay, so how do I explain it? Let's say that you have a pendulum, okay? Let's say that you have a pendulum and your pendulum is oscillating, right? And it's going to move to this place, okay? And it's going to move a certain angle. I hope you can believe me when I say that this pendulum is symmetric around this angle. It has rotational symmetry, right? Because you can rotate the whole thing by some degrees, and it's still the same pendulum, right? It didn't change. And so it's Lagrangian. If we write a Lagrangian to describe this pendulum, it's going to be, we are going to need to use this variable, this angle, right? So far, so good. But here's the thing that Emin-Noether discovered. Since this pendulum it has rotational symmetry, then this Lagrangian will also have rotational symmetry. And the way you can look at it is that what if we wrote this Lagrangian in terms of another angle? Let's call it alpha, right? No, I don't want to call it either. Let's call it just theta prime, okay? And I'm gonna say that theta prime is equal to theta plus epsilon. And epsilon can be anything. It's just something that is affecting this. If I write the Lagrangian in terms of theta prime, guess what? It's going to be exactly the same as it was before. Because in the same way that rotating the pendulum doesn't change it, is symmetric, well, this is basically like you are rotating the Lagrangian. You are moving, the Lagrangian had some value for the angle, and then you change it. So basically you rotated the Lagrangian, but the Lagrangian didn't change because the pendulum didn't change. So that's what's basically Emin-Noether's discovery. But also, she discovered that the way this is conserved is because there has to be a quantity in the Lagrangian that doesn't change. And in this case, that's angular momentum. So basically, whenever you have a system, if that system has a symmetry, then that Lagrangian will also have that symmetry, and it will have a conserved quantity, a quantity that doesn't change, in this case, angular momentum. And as you can imagine, that's extremely useful for scientists, because since these quantities do not change in your experiments, you only have to measure them once. And that's extremely useful, and you can use conserved quantities as your guide in your experiments to try to figure out what's going on. So, okay. I'm an author with her discovery about the Lagrangians, because before, thanks to Hamilton and Lagrange and Euler, we knew that Lagrangians were useful. But Emmy Noether revealed us why they were useful. And they become even more important once we go to quantum field theory. Because, okay, so how do I explain this? Turns out that, okay, all of this was in the realm of normal physics that you and I experience every day. But as you probably know, there's quantum physics, which is weird. And turns out that in physics, you can also use the Lagrangian, or rather, well, it's not exactly a Lagrangian, it's a Lagrangian density, and some people are very special about that. So let's say that this is the Lagrangian density, it's like an L. It's basically a Lagrangian, don't let people fool you. But anyway, the thing is that Noether's theorem is really important for quantum mechanics, because in quantum mechanics there are also symmetries, but also those symmetries are broken. And okay, let's just talk a little bit about how symmetries break. Because when I first learned about symmetries breaking, I was very confused. I was like, I learned all this time learning about symmetries, and now you're telling me they don't even work, they are broken, what's going on? And so, but it's nothing to be scared of. And let me explain. So for example, let's consider the sun. Okay, this is the sun, and then our planet, the Earth, is moving around the sun. And let's say that it's moving in a perfect circle, if I was able to draw a perfect circle, okay? And so, you know that circles have rotational symmetry. I hope that's not very controversial, right? Circles have rotational symmetry. But you know what also has rotational symmetry? Newton's law of gravity. Let me write it here. So Newton says, he discovered that the force of gravity between two objects is equal to the gravitational constant times their masses over the square of the distance between them. And here we have a minus sign because the gravitational force is always attracting, but the masses are always positive. So that's it. And we say that it has rotational symmetry because look, it only cares about the radius. It only cares about the distance between the objects, and it doesn't care where they are. Like the Earth might be here, or it could be here. Doesn't matter. The force is exactly the same. Rotational symmetry. Nice. But as you have probably heard, the orbit of the Earth isn't exactly a circle. It is more of an ellipsis. Now, in practice, it is pretty much a circle. Like it's like you look at it and you say that's a circle. But let me put another example of like, let's say, well, here we have also the sun, because I don't have much space to draw here. And let's say Pluto. I think Pluto does have a pretty elliptical orbit. Or, I don't know, let's say that this is just some other planet or a comet or... Yeah, a comet. Comets are a better example. Let's say that we have a comet here. Let's say that it's here. And comets do have orbits that are more elliptical. Now, actually no, let me draw it again. Sorry, one last time. Let's say that it's here the comet, and we draw it like this. Okay. So this is a more elliptical orbit. Now this doesn't have rotational symmetry because this radius is very different from this radius here, right? The distance is completely different. But first notice that, how do I explain this? The gravitational force still has rotational symmetry. That didn't change. So a physical object doesn't have to have the same symmetries as the equations that describe it, right? For example, this comet here, the force of gravity still has rotational symmetry, but the orbit of the comet doesn't have it. That's fine. Like the laws of nature have to abide by their symmetries very strictly, but the objects in the universe don't necessarily have to. But check this out. Even though the comet, even though its orbit doesn't have rotational symmetry, you know what it does have? A reflection symmetry, like we saw at the beginning. Remember this thing? It also had a reflection symmetry. And it's interesting because remember that I said that circles also have, like circles have rotational symmetry, sure, but they also have reflection symmetry. So my point here is that this system here, it has a symmetry, and its symmetry is a special case of the symmetry of the equations that describe it. See? Okay, let me be more explicit about this because this is important. So we have Newton's law of motion. Sorry, Newton's law of gravity, right? M1, M2 r squared. And the symmetries it has rotational symmetry, but it also has reflection symmetry. And actually, like, you can think of reflection symmetry as a special case, right? Because if something has rotational symmetry, it has to have, you cannot have rotational symmetry if you don't also have reflection symmetry, right? Reflection. But you can have reflection symmetry and not have rotational, right? It's like, think about it this way. Reflection symmetry is inside rotational symmetry. Actually, let me draw that. Actually, that is good. We have here, this is rotational symmetry. And it contains reflection symmetry. It's like a subset, reflection. But there are many other symmetries that can be here, other special cases of rotational symmetry. Okay, so my point here is that a system doesn't need to have, like, let's call this like the mother symmetry, and this is the daughter symmetry. In this case, of like this comet going around a star, it has to have one of the daughter symmetries of the equation, okay? And that's you can take this to the bank. Anything in nature, anything, will have at least one symmetry. And that one symmetry will be a special case of the symmetries of the equations of motion that describe it. And I mean, I guess I could try to prove that mathematically, but it would take me a long time. And just take my word for it. And if you want to prove it for yourself, go ahead. It's not. If you know enough mathematics, it's not that difficult to prove this. And so, well, anyway. So what's my point? Symmetries are broken all the time in nature. Like planets do it all the time. And so it's not surprising that the universe also has symmetries that are being broken, but at a more fundamental level. Hello, Fer from the future here. Apparently I did end up editing this video after all. At this point I started explaining a lot about how symmetries are broken in quantum mechanics, and that explains how we have particles and stuff. But honestly, I realized that the quality of that later half of the video, yeah, it was a half of the video, it wasn't as easy to understand, it wasn't as well explained as everything that came before. I guess it's a combination of me being tired of trying to record this video several times, I wanted to keep it simple, but it's a really complex subject, stuff like that. And so in the end, I thought it was just better just to cut that half. It just, believe me, it was really difficult to understand. It wasn't as well explained as the first half is. or if you think the first half is not well explained, this was even worse. And so yeah, this is the end of the video. So yeah, thanks for watching. Though if you want me to, if this video does well, I'll make more. Like I feel like I could talk about symmetries in physics for years. And so yeah, maybe if people find it interesting, maybe I'll make more. And I'll I'll make a better explanation of the symmetries in quantum mechanics and stuff like that. And so yeah, thanks for watching. And well, this video is meant to be useful like for students and stuff like that. And so like if you are studying something of science, not necessarily physics, it can be anything else. But if you are studying something of science and you watch this and it was useful to you, but please let me know, because that was my goal with this video. And so yeah, and let me know what you thought of this video regardless of anything. I want to know if it works, if I really manage to explain symmetries in physics in an approachable way. I know I didn't go into much detail, but I hope I just gave you the insights you need to develop a deeper understanding. And so, well, yeah, I think it's like the third time I say it, but yeah, thanks for watching and goodbye.